Okay, in this chapter, we're going to be talking about conformational and analysis and strain, primarily within alkane molecules. Okay, if you recall the discussion previously about the bonding in alkanes, you remember that alkanes are composed primarily of sigma bonds, just like we see here. And notice that if you rotate around the sigma bond like this, kind of like a propeller on an airplane, that you don't really do anything to the degree of overlap. So the bond is not affected by this type of rotation. Okay, so in a sense, we can have relatively free rotation around a carbon-carbon sigma bond. As we'll see in a few minutes, it's not completely free, but it's pretty close to being free. Okay, so let's take that compound there. Let's imagine that we're going to take a flashlight and just shine a light on this compound here, and we're going to call this representation right here a Sawhorse projection, okay? Because it looks kind of like a sawhorse. All right, when we shine the light, what we'll notice is that every CH bond on the right carbon is in the shadow of the CH bond on the left carbon. Okay? We're going to call this form of ethane eclipsed because of that. There's an eclipsing interaction, okay, just like a astronomical eclipse. The CH bond on the right carbon is eclipsed by the CH bond on the left carbon. In this form of ethane here, the CH bonds on these two carbons are as close to the CH bonds on the other carbon as they can possibly get. Okay, let's look at another extreme, and to do this, what I'm going to do is just do the rotation I did up there, rotate around that CC bond, and what you see here is the form of ethane at the very bottom of the screen here. Okay, in this form, we have the maximum separation of CH bonds on the right carbon from the CH bonds on the left carbon. And we're going to call this form the staggered form. Eclipsed and staggered are what we call conformational isomers, or conformers. They can be interconverted by an allowable bond rotation. If we look at what does ethane look like at room temperature, it's actually a very rapidly rotating molecule. In fact, it's rotating so fast that if you just looked at it, it would be a blur. Okay, so we cannot really separate and isolate eclipsed and staggered ethane. These are just two conformations that are, this is a process this interconversion is rapidly happening at room temperature. I'd like to also add that eclipsed and staggered are really the two extreme conformations. The only reason I drew these two is because they represent the extremes. They're as close as you can possibly get the CH bonds on adjacent carbons, and they're as far in the eclipsed and in the staggered, they're as far away as they can possibly be. There's an infinite number of conformations that are halfway, or some intermediate to some degree between staggered and eclipsed. Okay? All right. Let's look at representing this another way. And guess what we're going to call this? There's a hint there. That's the picture. That's our favorite postal employee, Newman. These are Newman projections. Okay, so let's imagine that I take ethane here, and I'm going to turn it on its side like this. Actually, I'm turning it kind of more like this, okay, around that axis right there. And this is the Sawhorse representation that I'll get after doing that. if you look at this Sawhorse representation that I've circled here, you can sort of see that if you're looking with your eye totally lined up with the CC bond, okay, you would see something like this picture right here. And this is the Newman projection. Okay, this is what a Newman projection is, named after Professor Newman at Ohio State, not the character on Seinfeld. Okay, all right. So in a Newman projection, you're representing the front carbon as the intersection of these three bonds right here, and this point right here defines the front carbon. The back carbon is this huge circle right here. In this picture right above it, I'm going to define something called the dihedral angle. Okay? And this is actually, most of the angles that you've seen in your life before are defined by 3 points. This is defined by 4 points. Okay? For example, we're going to look here at the projection angle between HA, the carbon HA is attached to, the next carbon, and HD. Our dihedral angle is the angle right here, and this is 60 degrees. When something is 60 degrees in a staggered conformation, it's referred to as being in a gauche orientation. Okay, HF is also in a gauche orientation with HA. The hydrogen that's different is HE. Okay, so HAC to C to HE. This dihedral angle is 180 degrees, and when something's 180 degrees in the staggered conformation, we're going to refer to it as being anti, or 180 degree dihedral angle. Much harder to draw is a Newman projection for an eclipsed conformation. This doesn't look perfect, as you can see. Everything has to be skewed. If it was a perfectly eclipsed conformation, HA and HB would be right on top of each other. Okay, in an eclipsed conformation, when the two species that we're looking at overlap perfectly, either dihedral angle is 0, we just use the term eclipsed to describe that relationship. Okay, it turns out that the rotation in ethane is not completely without a barrier. Okay? The eclipsed conformation is 12 kilojoules per mole higher in energy than staggered. In fact, staggered is the most stable conformation of ethane, and eclipsed is the least stable conformation of ethane. Say from this, it takes about 4 kilojoules per mole to eclipse 2 CH bonds. This destabilization is known as torsional strain or eclipsing strain. Okay, a lot of students seem to be confused about torsional strain versus other types of strain, but the key point to realize here is that you do not have torsional strain unless you have an eclipsed conformation. So this is only in the eclipsed conformation. Okay. All right, let's look at what this means as far as what is the distribution between staggered and eclipsed and all the other intermediate conformations. This is a very important equation here. I say that this is the most important thermodynamic equation in organic chemistry, that delta G equals minus RT-ln of the equilibrium constant, or if you want to algebraically turn that around to solve for equilibrium constant, it's the KEQ equals e to the minus delta G over RT. What this means is that the most stable species is favored at equilibrium. This is one of many situations where we're going to see this relationship, the most stable compound being the more abundant one. And it's a simple law of thermodynamics that tells us that this has to be the way. Okay, you see this temperature term here, and this just means that as the temperature gets higher, the equilibrium constant gets closer and closer to 1 to 1. Okay, so you see more of the lower energy one at lower temperature. At room temperature and well below, ethane is rapidly undergoing a rotation around the CC bonds, but if you had a camera with an extremely fast shutter speed, and this would have to be extremely fast, you would find that almost all of the ethane molecules are staggered. Okay, if you actually solve this equation and use 12 kilojoules per mole at room temperature, you'll find that the equilibrium constant is huge. Okay, all right, we're not ever going to solve that equation in organic chemistry. We're just going to use this as a qualitative relationship for explaining reaction dynamics. Okay, what's the origin of torsional strain? There's two theories. This one on the left is probably the older one, stating that because of the electrostatic repulsion between two electron pairs, you don't want to get them too close to each other. And this is, I guess this was the first explanation for torsional strain. This has largely been replaced with a molecular orbital based explanation. And this one on the right says not what's bad about Eclipse. It says it's really trying to explain what's good about staggered. Okay, so in staggered we can have this weak molecular orbital interaction between the sigma star of this CH bond right here and the sigma of this CH bond right here. Okay, so we're taking the sigma, which is filled, and the sigma star, which is empty. Okay, here is a molecular orbital diagram that shows this, and what we see here is a little bit of a stabilization. Actually, there's three of these stabilizations here because there's three CH bonds. But only staggered can have this stabilization because only here do you see the perfect overlap of sigma and sigma star. Okay, so this is largely considered the more accepted explanation. It's not what's bad about Eclipse, but what's good about staggered. Okay, let's look at a more complicated molecule, and we're going to look at butane. When you think about this, you're probably initially saying, okay, the Newman projection, I have to draw the front carbon as a Y and the back carbon as a circle, but there's 4 carbons in butane. What do I do? Well, you need to have another set of directions, and this is which bonds to cite, which bonds to make the Y in the circle. Okay? The most interesting conformational situations occur when you cite the C2-C3 bond of butane. Okay, so let's butane. Just for reference here, CH3, CH2, CH2, CH3, and the IUPAC numbering system would be like that. Okay, if you cite the C1, C2 bond, you get this Newman projection down here. This one is really less interesting. The only thing we have going on here is staggered and eclipsed. It's the same general issue that we saw with ethane. Okay, all right, so I'm going to start off by drawing this conformation of butane. And this is called the anti-conformation. In the next slide, we'll look at some of the beautiful effects in the anti, but this is the most stable conformation. I'm going to go through a series of 60-degree bond rotations of the back carbon counterclockwise. So we're going to take the back carbon and rotate each of these by 60 degrees. All right, what this gets me to is this next conformation, which we're going to call partially eclipsed. And the energy of partially eclipsed relative to anti is 14 kilojoules per mole. So it's 14 kilojoules per mole higher in energy. Okay, now I'm going to do another 60-degree rotation. Okay, so we're going to rotate this here, this one to here, and this one to here. Okay, when we do this rotation, this gets us to another staggered conformation, which is called the Gauche Conformation. The Gauche Conformation is only 3 kilojoules per mole energy higher than the anti. We'll talk about the reason why it's a little higher in just a second. But notice how, if we look at the staggered conformations here, it's the Gauche and the anti, and these are at our lowest energy values. Okay, finally we're going to do the last of these 60-degree rotations. Okay, and this is going to get us to the worst or highest energy conformation of all, the fully eclipsed form. This is actually not very stable at all. It's 32 kilojoules per mole higher in energy than anti. Okay, so let's look at the destabilizing effects of these conformations. Okay, so I have anti at the bottom here, but we won't appreciate its beauty until we look at all the nasty things going on in the other ones. Okay, so the Gauche conformation is staggered, and remember that it's plus 3 kilojoules per mole relative to anti. Okay, what's destabilizing the Gauche relative to anti is that these methyls are getting close to each other. I just typed out the word Me, but that doesn't really do justice. They have to occupy a certain space with the carbons and the hydrogens. Okay, and what we see here is that they're getting close to each other. And we use this symbol here. It's a little bit obscured. I'll show it here on the fully eclipsed. And this is used to show that two species are getting too close to each other. This is a sign that we have something called a steric strain in our molecule. Two things are wanting to occupy the same space at the same time. Okay, so they can't do that. Their electron pairs are getting crammed into each other. So this is a destabilizing situation, not nearly as destabilizing as if it were eclipsed. Okay, let's look at partially eclipsed. Here there's a lot of torsional strain because it's an eclipsed conformation. It looks like the eclipsing of CH is a little worse than eclipsing an HH. This is plus 14 kilojoules per mole relative to anti. And remember, when we're looking at ethane and they were all hydrogens, it was only 12 kilojoules per mole higher in energy. Okay, fully eclipsed. If Gauche is having a steric interaction, the steric interaction in the eclipse is obviously going to be a lot more severe. The methyls have become as close as they can possibly get. Okay, so because of this conformation is extremely destabilized. Okay, And again, because of delta G equals minus RT ln KEQ, we know that at equilibrium, almost all of the molecules of butane would be anti. There would be some of them, however, that there would be several of them that were gauche, and probably very few that were partially or fully eclipsed. Okay, notice the anti-conformation avoids all steric interactions and all torsional strains since it's a staggered conformation. The methyls are too far apart to interact sterically. Okay, so we're going to end this section here by doing a problem. Draw the most stable conformation for 1,2-dichlorobutane, citing the C1-C2 bond. Assume that methyl and ethyl are larger than chlorine, and that sterics are the dominant force determining stability. What you should do right now is pause it and do this problem yourself, and then restart it after you've done the problem to verify whether your answer was correct. Okay, the IUPAC numbering system would be as so. So we're going to use these two carbons as the Y and circle in the Newman projection. Okay, why? Because it's shaped like the letter Y, not because I'm asking the question why. All right, so sometimes, let's go back a second. Students always ask me, where do I start? And they're sort of worried about drawing the right conformation the very first time. So where do you start? The answer is somewhere. Usually when you are asking for the most stable, this is a clue that you should be drawing a staggered conformation and not an eclipsed conformation. Okay, so let's not even consider eclipsed conformations. We're just going to draw one staggered conformation and then do a series of 120-degree rotations to make sure that we've looked at all of the possible conformations. Okay? All right, so here's the Newman projection. Here's carbon 1, carbon 2, carbon 3, and carbon 4. Okay, so I'm just arbitrarily going to draw chlorine right there. Okay, I'm going to go through a series of rotations. Looks like I'm rotating counterclockwise, 120 degrees at a time. Okay, so this next conformation I'm going to get is this one. And finally, I'm going to do that same rotation, and I'm going to get chlorine down here. Okay, what we want to do is count up the Gauche interactions. Chlorine with chlorine, chlorine with ethyl, chlorine with chlorine, and chlorine with ethyl. Okay, so we can probably narrow it down to one of these two conformations as being the most stable because of the fewer number of Gauche interactions. All right, we need this statement here to finish the problem. Methyl and ethyl are larger than chlorine. This is a chlorine-chlorine Gauche interaction. It's not as severe as this one, which is a chlorine-ethyl. Remember, ethyl is larger than chlorine. So this is going to be the more severe Gauche interaction. Okay. All right. Because of that being more severe, that's going to mean that this conformation in the middle is going to be the one that we select as being the most stable conformation. Fewer Gauche interactions, and the Gauche interactions that you do have are less severe. Okay, here's a question for you. Which conformation is the least polar? Okay, the only serious dipole you would have here would be coming from the carbon-chlorine bonds, so we could say that this one would be the least polar. Okay, I'm going to end this video right here. And let's see, escape. Okay, it's very loud, sorry.